talking about how we can represent complex numbers on a graph, on a piece of graph. Now we already know that we can represent real numbers on the real number line. So we have this real number line. Let's say this is positive x. Let's say this is positive infinity. This is positive infinity. This is, if I put the positive sign over here, this is negative infinity. Somewhere between these two limits, somewhere between these 2 points, we have the origin of everything, the origin of the universe, so as to say. That would be the point 0. Let me just keep it as such. There will be numbers like 1, 2. We would have negative numbers, -1, -2. We can have rational numbers, we can have fractions. So if this is 3, somewhere around here would be 2.5. We can also have irrational numbers like pi and e, points like that. And all of them can be represented on the real number line, right? Now, if we can represent real numbers on the real number line, why should complex numbers be left out? Complex numbers should also be represented, or at least they should be able to be given a position on the graph paper, right? Now, where do we place a number which looks like this? Let's say we have a complex number z equal to 1 plus I. So 1 plus I is actually 1 plus 1i, which means the real part is 1 and the imaginary part is 1i. So what and how do we represent this complex number on the real number line? The first question that would come to my mind is, this is the real number line, right? This is the real number line. So let me just write that down. This is the real number line. The question arises, how can I represent a complex number, mind you, which is not a real number? This number does not belong to the set of real numbers. So why and how should I represent a complex number which is not a real number on the real number line? I'm trying to push in something which is not part of this set. This is, let's say this is the set of blue books, and I'm trying to put in a red book. It will not fit in, right? It will have to be given another position, it will have to be given another shelf. We need to look for a way to incorporate this sort of number into the graph paper. I wouldn't say the real number line, but the graph paper. Now we need to find a way for that. When we look at a complex number, we notice, as we have mentioned in the previous video, complex number has two parts. A real part, which is here marked by yellow, and we would have an imaginary part. So that's the blue part. So a complex number is a composite number which consists of two parts. It has a real part and an imaginary part. So it has two parts. Now we need to represent both these parts on the graph paper. How can we represent two numbers on a graph paper? Now, the first thing that would come to my mind is, let me look at two dimensions. So we know of the coordinate system, right? The x-axis and the y-axis. So let me just draw that and see if I can, adjust our concepts and adjust our knowledge domain so as to fit what we need. Yeah. Let me go back to the complex number that I have. So that's 1 plus 1i. Now I have to structure the plane that I have. So let's say this is the origin. So that is represented, when we talk about the coordinate system, that is actually 0, 0. We'll be adjusting the meaning and the representation soon to accommodate the concept of complex numbers. This would represent positive x, or rather positive x on the infinity side. This would represent minus x. This direction would represent positive y, and this direction would represent negative y. That's something that we know already. And any point can be represented on this plane. So if we have 1, if we have 2, if we have 3 on the x-axis, and if we have 1 and 2 on the y-axis, somewhere around here we would have a point 3, 2, right? This is something that we know. Now, how can we use this concept to represent complex numbers? Let me just change the color. The first thing that we would have to do is rename this plane. This cannot be called the coordinate system, the normal coordinate system that we call, this has to be renamed to something called the Argand plane. Now, when we hear the term Argan Plane, we have to think that this is no more the usual coordinate system that we know of. This is the plane on which we represent complex numbers. It's not just mere points that we are talking about here, they are complex numbers. They are concrete complex numbers, a composition of a real number and an imaginary number. But if that's the case, then shouldn't every point be representing a complex number? That's right. Every number here should represent a complex number. So what does this origin represent? This origin represents, say, a complex number z0, which is actually 0 plus I0. This is a complex number too. It's a real number too. I am not denying that, because the imaginary part is 0, which essentially means that it doesn't have an imaginary part, but this is still a complex number actually. So we can represent the complex number 0 plus I0 on the Argand plane. That's the origin for everything. So what does this complex number represent? Now we can see that this is the point 3 comma 2. So it should either represent z equal to 3 plus 2I, or it can represent 2 plus 3I. Up until now, from what we know, I cannot barely say which one it is. Is it 3 plus 2I or is it 2 plus 3I? To solve this dilemma, let us look at what we have up until now. Now, usually, this is called the standard form. So, in our standard form, when we write a complex number, we write the real part first, and then we write the imaginary part. So, for any complex number written in standard form, we'll have the real part first. So, we'll have real of z. This is called the real part of a complex number z. So, z equal to real plus z, real of z, plus the imaginary part of z times I. Now, when we talk about this complex number, if it follows the standard form, which it does, then this should represent the real part and this should represent the complex part. If that is true, then this should be the first point, right? It's in standard form. So this should be the real axis. This should represent the real numbers. And this should represent the imaginary part. This should be the imaginary part, right? The first number will represent the real part and the second number will represent the imaginary part. So this is the real number, which means the point 3 should be on the real axis and the point 2 should be on the horizontal axis, not the other way around. We wouldn't have this, because for that, this point would represent, let's say this is 3, we would have it somewhere around here, because in this case 2 is the real number. 2 is the real number and 3 is the imaginary number. So this point somewhere around here would be represented by this complex number, and this point represents this complex number. So we can represent any complex number as follows. Now there are other ways in which, and there are other concepts that follow from the Argand plane, but basically any complex number that you can think of, any complex number. Let's say you can think of, if this is -1, if this is -2, this point would represent approximately -2, 1. That would be the complex number z equal to, the first part is real, so -2, the second part is imaginary, so plus I. Let's say you have -1, this is -1, this is -2, this is -3, so we can have somewhere around here the point -3, -2 comma -3, so the x-axis goes first. So we'll have somewhere around here the complex number -2, which is the real part, -3, which is the imaginary part. Again, this would be the point 2 comma 2, so no, rather it will be the point 2 comma -2. So that would be representing the complex number, pardon my writing. This would be the complex number, the real part is positive, so 2, the imaginary part is negative, -2i. So we have a lot of complex numbers, right? 3 plus 2i. We have the complex number, this is 2 plus 3i. I didn't need to be cut. This is the point 2 plus 3i. This is the point minus 2 plus I. This is the point 0 plus 0I. This is the point minus 2 minus 3I. And finally, we have the point 2 minus 2I. So we can think of many complex numbers that we can fit on the Argand plane. Now, and that is how we represent complex numbers on a graph paper on the two-dimensional plane.